Hey everyone, welcome back for another deep dive. Today we're going on a journey into the amazing world of semiconductors.
They're pretty incredible, really, when you think about it.
I mean, they're the foundation of all modern electronics.
Right.
And I feel like most people they don't even give a second thought to how these tiny components actually work.
Yeah.
So I thought, today we could shed some light on the magic that makes these little marvels possible. Start with the fundamentals.
Sounds good.
So when we talk about semiconductors, we're really diving into the world of electrons and how they behave within these materials. It's different from how they act in, a single atom.
Yeah, it's a whole different ballgame when you've got billions of atoms all packed together in a solid.
Right. So I remember from, basic physics, electrons in an atom, they occupy those specific energy levels. But what happens when you bring all those atoms together in a solid?
Ugh. Well, you can picture it like this. Imagine each atom's energy levels as like individual houses.
Okay.
And then when the atoms come together in a solid, all those little houses, they start to overlap. Like they form these entire neighborhoods of energy levels.
Okay.
And we call those neighborhoods energy bands.
So instead of having those, distinct energy levels, you now have these continuous bands
Exactly.
where the electrons can hang out.
Yeah.
That's a cool visual.
Yeah, and it's just like in a real city.
Yeah.
You know, some of those neighborhoods, they're more desirable than others.
Right.
So you've got, for example, the valence band. That's kind of like the suburbs. That's where most of the electrons are just kind of chilling out,
Yeah.
participating in chemical bonds, holding things together.
Right. So they're comfortably settled there. They're not really moving around too much.
Right. Yeah, exactly. They're kind of stuck in their little houses in the suburbs. Then you have the conduction band. Now that's downtown. That's where the action is.
Mhm.
And that's where the electrons are free to move around and do their thing. Conduct electricity.
So those are the free spirits, the ones that are zipping around and making all the electronic wizardry we love possible.
Exactly. They're the ones that make our phones and computers work.
Yeah.
But there's a catch. There's a barrier between these two.
Okay.
You can't just go straight from the suburbs to downtown.
Okay.
There's a forbidden zone. We call it the forbidden energy gap or band gap.
So there's like a wall between the suburbs and downtown. The electrons can't just cross over.
Exactly. It's like a no electron zone.
Okay.
And the size of this gap, this is really important because this determines whether a material is a conductor, a semiconductor, or an insulator.
Oh, that's interesting. So this energy gap is like the key to understanding how materials conduct electricity.
It is, yeah. So conductors, like copper, they basically have no gap. It's like a wide open highway for electrons. They can zip around freely.
Okay, so conductors are like the electron superhighway.
Yeah, a perfect analogy.
Okay.
And then you've got insulators, like rubber. Now they have a huge gap, like a giant mountain range that the electrons can't get over.
Right. So it's like trying to drive through the Himalayas.
Yeah, exactly. You're not getting anywhere fast. And then right in the middle, you have semiconductors. They have a gap that's not too big, not too small, like a toll booth on the highway. Electrons can pass, but they need a little push.
A little encouragement.
Yeah, exactly.
Okay.
And a great example of a semiconductor is silicon. It's the superstar of the semiconductor world. And its little gap is what makes it so special.
Yeah, silicon's in everything these days.
Yeah.
So this small gap, it allows us to control its conductivity.
Yes, precisely, in really cool ways.
Okay, so we've got conductors with their free-flowing electrons, insulators with their tightly bound electrons, and then we've got semiconductors somewhere in between.
Right.
But I've always been kind of mystified by this concept of holes. Like, what are they? How can something that's not there actually contribute to the flow of electricity?
I know, it sounds strange, doesn't it? But holes are actually super important.
Okay.
When an electron, jumps from that valence band to the conduction band, it leaves behind a little vacancy, a missing negative charge.
Mm-hmm.
And that vacancy, that absence of an electron, it behaves like a positive charge, and we call that a hole.
So it's like if you have a parking lot full of cars and one car leaves, it creates an empty space.
Yeah. And that empty space, that's the hole. And it can move around as other cars move in and out of the parking lot.
Okay, so it's not really a physical thing. It's more like the absence of something.
Exactly. But it acts like a positive charge carrier.
Right.
And so as the electrons move one way, these holes seem to move the other way, both contributing to the flow of current.
It's like a dance between electrons and these phantom holes.
Exactly. It's a very intricate dance.
So we have both electrons and holes contributing to conduction, but in opposite directions.
Yeah.
This semiconductor dance is getting more and more intriguing.
It is, isn't it? And it gets even more interesting when you factor in things like temperature.
Oh, yeah. I've definitely noticed that. Like, my phone seems to drain way faster when it's cold outside. Does temperature actually affect how semiconductors work?
Oh, yeah, absolutely.
Okay.
At absolute zero, a semiconductor is like an insulator. All the electrons are locked in place, like they're frozen in a giant ice cube.
Right.
But as you warm things up, some of those electrons, they gain enough energy to break free from their bonds and jump to the conduction band, so you get more free electrons and more holes.
So it's like adding heat to that parking lot and some of the cars are suddenly able to move around?
Exactly. The more heat you add, the more free those electrons and holes become, and the better the material conducts electricity.
Okay, so higher temperatures make semiconductors more conductive. But we also have another way to control their conductivity, right?
Yeah.
Through doping.
You got it.
Doping. That sounds like something you do to athletes, not materials.
I know, right.
But it's basically adding impurities to a pure semiconductor intentionally
Right.
to fine-tune its conductivity. I never would have thought of that.
Yeah.
Like, wouldn't we want them to be as pure as possible?
You'd think so, but actually adding those impurities, it gives us this amazing level of control over how the semiconductor behaves.
Like we're adding secret ingredients to a recipe.
Exactly. We can make it more conductive or less conductive, depending on what we add.
Okay.
So there are two main types of doping. We have N-type doping and P-type doping.
Okay, so N-type and P-type, what's the difference?
With N-type doping, we add impurities like phosphorus or arsenic. These guys have 5 valence electrons. And when they replace a silicon atom in the crystal structure, they bring an extra electron to the party.
So N-type doping is like releasing a bunch of extra electrons into the material, making it more negative.
Exactly. More free electrons means more conductivity. Now with P-type doping, we add impurities like boron or aluminum. They only have 3 valence electrons.
Okay.
So when they bond with silicon, they leave behind a hole, a missing electron. And those holes act like positive charge carriers.
So it's like we're creating those empty parking spaces.
Yeah. And the more empty spaces we have, the more holes can move around and the more conductive the material becomes.
Okay, so N-type doping adds extra electrons, and P-type doping creates more holes.
Precisely.
And by carefully choosing the right impurities and how much to add, we can essentially engineer the semiconductor's conductivity to be exactly what we need for a specific application.
Exactly. It's like we have a set of dials that let us fine-tune how well the material conducts electricity.
That's incredible. But what happens when we bring these two types of semiconductors together? An N-type and a P-type.
Oh, that's when things get really interesting. That's where we create something called a PN junction.
A PN junction.
It's the heart of many electronic devices, from diodes to transistors. Imagine you have 2 crowds of people. One crowd has way more electrons than holes,
Okay.
and the other crowd has way more holes than electrons.
Right. So one's like N-type and the other's P-type.
Exactly. What do you think happens when those 2 crowds meet?
Oh, I have a feeling things are about to get pretty wild. I can't wait to find out. But we'll have to save that for part 2.
Oh, it gets wild, all right. When a P-type and an N-type semiconductor come together, it's not just like a casual meet and greet. It sets off this whole chain reaction.
Oh, okay. So what happens when these two semiconductor worlds collide? What goes down?
Well, you know those crowds we were talking about?
Yeah, the crowds with the electrons and the holes.
Right. So the electrons from the N-type side, where they're all hanging out, they're naturally attracted to the P-type side, where there are all these holes just waiting to be filled.
Right, because opposites attract.
Exactly. It's like a massive electron hole mixer.
But, I mean, does this electron hole shuffle just keep going on forever?
Not exactly. As the electrons and holes diffuse across that junction, they leave behind these immobile ions, you know, the charged impurity atoms.
Okay.
And those ions create an electric field. It's like a kind of border patrol that tries to stop any further diffusion.
So it's like the party gets a little too crowded, and a bouncer shows up to keep things under control.
Exactly. That's a great way to put it. And that electric field creates this region near the junction called the depletion layer.
Depletion layer.
Yeah, it's basically a zone where there aren't many free charge carriers. It's like a buffer between that electron-rich N side and the hole-rich P side.
So there's this kind of standoff happening within this depletion layer.
Yeah, it's like a constant tug of war. The electrons and holes want to mingle, but this electric field is trying to keep them apart.
Okay.
And the electric field sets up this potential barrier. You can think of it like a wall that prevents further diffusion.
Okay, so there's this wall Or potential barrier, but it's not like a physical wall. It's more like an energy
Yeah,
barrier.
exactly. It's like an energy hill that the electrons and holes have to climb over to get to the other side.
Okay.
And the height of that hill, that potential barrier, it depends on what types of semiconductors you're using. Like for germanium, it's about zero point 0.3 volts.
Okay.
But for silicon, it's closer to zero point 0.7 volts.
So silicon junctions are a little more exclusive than germanium ones.
You could say that, yeah.
But here's a question. Can we mess with this potential barrier? Like, can we make it easier or harder for those charge carriers to cross?
We can. And that brings us to the concept of biasing. It's basically applying an external voltage across that PN junction.
So we can become like electron traffic controllers.
Exactly. We can either help those charge carriers cross, or we can make it even tougher for them.
Okay, so how do we make it easier for them to cross?
That's called forward bias. We connect the positive terminal of a battery to the P side of the junction and the negative terminal to the N side. And that lowers the potential barrier, makes that wall a little shorter.
So it's like opening the gates and letting the electron hole party resume.
Exactly.
Okay.
And with forward bias, all those majority carriers, the electrons on the N side and the holes on the P side, they can easily diffuse across the junction, and you get a nice flow of current.
Okay, that makes sense. So that's how we get current flowing through a PN junction.
Yeah.
But why would we ever want to make it harder for the charge carriers to cross? What's the point of that?
That's called reverse bias.
Okay.
And yeah, it might seem counterintuitive, but it's actually super important. We do that by connecting the negative terminal of the battery to the P side and the positive terminal to the N side.
Okay, and so that increases the potential barrier, makes it harder for those majority carriers to cross.
Yeah, it's like building an even taller wall between those two crowds. And in this case, you only get a tiny current called the reverse saturation current. It's mainly due to those minority carriers, the few electrons on the P side and holes on the N side.
Okay, but I'm still not clear on why we'd want to block that current flow. Doesn't that make the junction useless?
Not at all. This unique behavior under reverse bias, this is what makes diodes so useful.
Okay.
They basically act like one-way valves for electricity.
Ah, so they only let current flow in one direction and they block it in the other.
Right, like a door that only swings one way.
Okay, now that makes sense.
Yeah.
But what happens if we push things to the extreme? Like, what if we really crank up that reverse bias to, like, a crazy level?
Well, that's when things can get a little dramatic.
Okay.
At a certain point, when that reverse voltage gets high enough, the electric field in that depletion layer, it gets so strong that it can actually rip electrons from their bonds.
Whoa.
And that creates a whole avalanche of new electron-hole pairs. It's called, well, breakdown.
Breakdown. So it's like the dam breaks and a flood of charge carriers rushes through.
That's a great analogy. And there are actually two main types of breakdown. You have Zener breakdown and avalanche breakdown.
Okay, so two types of breakdown. Do they have different consequences?
They're similar in that they both lead to a sharp increase in current.
Right.
But Zener breakdown happens at lower voltages, where the electric field is strong enough to directly break those covalent bonds. Avalanche breakdown happens at higher voltages, where those minority carriers gain enough energy to knock loose even more electrons and create more electron-hole pairs.
So it's like two ways to break a dam. One is brute force, just overwhelming it with pressure, and the other is like setting off a chain reaction.
Exactly. And while breakdown might sound kind of catastrophic, it can actually be really useful.
Okay.
And that brings us to the world of Zener diodes.
Zener diodes. Okay, so we're talking about controlled chaos here.
In a way, yes. Zener diodes are specially designed PN junctions that actually take advantage of this breakdown phenomenon.
Okay.
They're heavily doped to have a very thin depletion layer, so breakdown happens at a very specific, predictable voltage.
So it's like engineering a controlled avalanche.
Exactly. And this property makes them super useful as voltage regulators.
Okay, so how does that work? How do they regulate voltage?
They can maintain a constant voltage across a load even when the input voltage is fluctuating.
So it's like a safety valve that prevents too much voltage from reaching sensitive circuits.
Exactly. That's one of their key applications.
Wow, that's pretty amazing. You know, I've always wondered about those characteristic curves we see for diodes. They always look so, I don't know, curvy.
Uh-huh. They do. That curve is basically a graph that shows how the current through the diode changes with the voltage across it.
So it's like a map of the diode's personality.
Yeah, you could think of it that way.
Can you walk us through some of the key features of that curve?
Sure. So in that forward bias region, initially the current increases gradually as the voltage increases. That's because that potential barrier is still pretty high. But then once the voltage gets higher than the knee voltage, usually around zero point 0.7 volts for silicon, the current really takes off.
So it's like the diode suddenly wakes up and starts conducting like crazy.
Exactly. Because that potential barrier is pretty much gone at that point, so the majority carriers can flow freely.
Okay, and what about in the reverse bias region?
In the reverse bias region, you have a very small current, almost constant, until you hit that breakdown voltage. And that tiny current is due to those minority carriers we talked about. But then, boom, once you hit that breakdown voltage, the current shoots up.
So it's like a long, flat road that suddenly turns into a steep cliff.
Exactly. That's a great way to visualize it.
Okay, this is all super cool, but I'm curious about, like, real-world applications. What are some things that diodes are actually used for?
Oh, they're used in tons of things. Rectifiers, for example.
Okay.
They convert AC to DC, which is essential for powering most electronics. And then there are clippers. They limit those voltage levels to protect those sensitive circuits. And clampers, they shift voltage levels, which is important for signal processing.
So they're like the unsung heroes of the electronics world.
I like that. They're quietly doing all these crucial tasks behind the scenes.
Okay. But we can't forget about transistors. Those tiny but mighty powerhouses. Tell me more about them.
Transistors. They are truly remarkable. They consist of 3 semiconductor layers, either NPN or PNP configuration.
Yeah.
And those layers form 2 PN junctions. We can bias those junctions independently to control the flow of current through the whole device.
So it's like having 2 diodes back to back, but with a special twist.
You got it. And the middle layer, it's called the base.
Base, okay.
Yeah, and it's super thin and lightly doped. And then the outer layers, those are called the emitter and the collector.
Emitter and collector, okay.
And they're more heavily doped.
And so how do those 3 terminals, the emitter, base, and collector, how do we use those to amplify or switch signals?
Well, that's where the real magic happens. In a typical amplifier setup, you forward bias the emitter base junction.
Okay.
And you reverse bias the collector base junction.
Wait, so we're applying both forward and reverse bias at the same time to the same device. How does that work?
It's pretty ingenious, actually. The forward bias across that emitter base junction lets a small current flow through the base. And that small base current, it controls a much larger current that flows between the emitter and collector.
So like a small change in the base current can lead to a big change in the collector current. It's like a tiny lever that's controlling a heavy gate.
Perfect analogy. And that's the essence of amplification. A small input signal gets amplified into a much larger output signal.
Wow, it's incredible how something so small can be so powerful.
It really is. And transistors aren't just for amplification. They can also act as switches. By changing those bias conditions, we can switch the transistor between an on state, where it's conducting current, and an off state, where it blocks the current.
So it's like having a tiny electronic on-off switch. Okay, so I'm starting to see how these transistors, they're like building blocks that lead to all the digital circuits in our computers and smartphones and everything. But how do we go from transistors to, like, the complex logic that makes those circuits work?
That's where logic gates come in. They're the brains behind those digital circuits. And they use transistors and other components to carry out those logical operations. But we'll have to save that story for part 3.
Okay, so we've gone from the world of electrons and holes in semiconductors to those PN junctions, diodes, and transistors. I'm ready to tackle those logic gates, the brains behind all those digital circuits we rely on so much.
Yeah, they're pretty fascinating. Logic gates, they're like the decision makers in the digital world, They process information based on these logical rules.
So we're not dealing with electrons and holes anymore. We're talking about signals, like true or false signals.
Exactly. Those signals, they're like electrical messengers carrying bits of information, ones and zeros.
Okay.
And those logic gates, they take those signals as inputs, and then based on a certain logical operation, they produce an output signal.
So they're like traffic directors guiding the flow of information.
Yeah, a perfect analogy. And there are 3 main types of logic gates, the basic ones, AND, OR, and NOT. Each one has its own little rule, its own way of operating.
Okay, I'm ready to learn the rules of the road for these digital traffic directors. Let's start with the AND gate. What's its deal?
Think of the AND gate as a really exclusive club.
Okay.
You only get in if you meet all the requirements.
Okay.
So in logic terms, its output is only true if both of its inputs are true.
So it's like needing both a ticket and a valid ID to get past the bouncer.
Exactly. If either input is false, the AND gate says, nope, you're not getting in.
It's a strict gatekeeper. Okay, so the AND gate needs both inputs to be true. What about the OR gate? Is it a bit more lenient?
The OR gate is much more welcoming, you know.
Okay.
It's happy to see you if you meet at least one of the criteria. So its output is true if at least one of its inputs is true.
So you could have the ticket or the ID, and you're good to go.
Exactly. Only if both inputs are false does the OR gate say, sorry, not today.
Okay, got it. So the AND gate is like a logical and the OR gate is like a logical or. What about the NOT gate? What's its rule?
The NOT gate, that's the rebel of the group, always likes to do the opposite. So its output is always the opposite of its input.
So if the input is true, the output is false, and vice versa.
Yep, that's it. It just flips the script like a light switch that's always the opposite of what you expect.
Okay, I think I've got those 3 basic gates down, but I'm guessing things get a bit more complex when we start combining them, right?
Oh yeah, for sure. We can combine those basic gates in all sorts of ways to create some pretty amazing logic circuits.
So it's like building a whole language using just a few letters.
Exactly. Like take the NAND gate, for example.
NAND gate. Okay,
It's basically an AND gate followed by a NOT gate.
okay.
So its output is only false if both inputs are true. Otherwise, it's true.
So it's like saying not both of these things can be true at the same time.
Exactly.
What about the NAR gate?
the NOR gate? That's an OR gate followed by a NOT gate. So its output is true only if both inputs are false. Otherwise, it's false.
Ah, so it's like saying neither of these things can be true. It's pretty amazing how we can create such complex logic just by combining these simple gates in different ways.
It is, isn't it? And
Yeah.
by doing so, we can build circuits that can do all sorts of incredible things, arithmetic, storing information, making decisions. It's what makes our computers and smartphones and all that digital magic possible.
Wow, we've come a long way from those basic energy bands and the dance of electrons and holes. Who knew those tiny components could lead to something so powerful and versatile?
It's really mind-boggling when you think about it.
It really is. This deep dive has been an incredible journey. I feel like I've gained a whole new understanding of the world of semiconductors and the logic that underpins our digital age.
Glad to hear it. And remember, the world of semiconductors, it's always evolving. There's always something new to discover.
Well, I can't wait to see what the future holds. And I definitely can't wait for our next deep dive. Thanks for listening, everyone.